In this video, I will go over the homework that follows the lecture 13.1 that covers the topic of improper integrals of type 1. And as always, I hope that you watched the lecture, and let's go ahead and jump right into the homework. And the first problem is we have an improper integral of type 1 with infinities in both limits of integration, and the way we address the issue of having infinities in both limits is by using the subdivision property and splitting the integral into two. So to do that, we have to pick a value. Normally we pick some nice value. When there is no preference, we can probably just go with 0 as a rule of thumb. Here I'm going to separate this integral into two. And now we're going to address the improperness of each of these integrals by introducing a new variable. So instead of negative infinity, I'm going to put t. And instead of infinity in the second integral, I'm going to put s. But to make this transition, we have to set it up as a limit. So here t goes to negative infinity, and here s goes to positive infinity. Now that we don't have infinities in the limits anymore, we can now focus on actually finding the indefinite integral. So since both of those integrals have the same integrand, we can do it all here. So we're kind of hitting the pause button here for a second. And let's find this indefinite integral. This one we probably are going to do by parts. U is x, dv is e to the negative x dx, so du is dx, and v is negative e to the negative x. And the integral is now uv, so it's negative x e to the negative x minus v du, so it's going to be plus integral of e to the negative x dx. And we are ready to produce the final answer here. That's the indefinite integral. However, we have definite integrals, and not only that, we also have limits. So now we're going to hit the continue button, I guess, and continue with the main solution. So we have limit as t goes to negative infinity of negative x e to the negative x minus e to the negative x from t to 0 plus limit as s approaches to positive infinity of negative x e to the negative x minus e to the negative x from 0 to infinity. So the first limit is negative, so we're going to plug in 0 first. So we have negative 0 e to the negative 0 minus e to the negative 0 minus and now we're going to plug in t. So we have negative t e to the negative t minus e to the negative t. And the second limit is going to be s goes to positive infinity, and we have negative s. I just made a typo here. This is s. So we have negative s e to the negative s minus e to the negative s, and we subtract at 0. 0 times e to the power negative 0 minus e to the power negative 0. And in order for the original integral to converge, both of these integrals have to converge. That means if at least one of them doesn't converge, then the entire integral doesn't converge. So here we can just do some simple math. 0 times anything is 0. This is just 1. But here we have e raised to the power negative infinity. So this is infinity. It's negative infinity. And we're plugging in another negative infinity. See, so it's not that clear actually. So we have infinity minus infinity there. And I think we can benefit here from actually simplifying it a bit. So let's turn this into 0, turn this into 1. So we have negative 1 plus I guess we should just take the constants out here. So we have negative 0 minus 1. So we have negative 1. Let's distribute the negatives. So we have limit t goes to negative infinity. And we have t plus 1 e to the power negative t. So I'm going to rewrite it as t plus 1 over e to the power t. Here we have plus limit as s goes to infinity. Same thing, we can take out the negative, and we have s plus 1 over e to the s. And we have minus negative 1, so it looks like plus 1. So negative 1 and 1 are reduced. And now as t goes to infinity, as t goes to negative infinity, the t plus 1 goes to negative infinity, but e to the negative infinity is actually 0. So this whole first limit is actually undefined, meaning the original integral diverges. And it doesn't matter what's going on with the second integral, although it's 0. So we're ready to answer the question. We believe that this integral diverges, and therefore we're going to enter that answer. All right, let's continue. We have another question. This time we have infinity only in one of the limits of integration. So let's introduce a new variable, send it to infinity, and let's get rid of that infinity in the limit. And here we can do some basic maintenance. We can take that 2 out, and we can acknowledge that 49 is 7 squared. And then this integral is actually a well-known formula, so it's going to be 1/7 arc10 of, I believe, x over 7. And we're evaluating it from 7 to t. So we can take the 7th out of the limit, and plugging in the limits of integration, we get arc10 of t over 7 minus arc10 of 7 over 7, which is arc10 of 1, which is pi over 4. But I think the main problem here is to find the limit of arc10 of t over 7. And here we have t approaching to infinity, and we know that arc10 of infinity is actually pi over 2. So this limit is pi over 2 minus pi over 4. So looks like it's just pi over 14. So let's go ahead and try that answer. Did I say 18? I meant, of course, 14. And we got it. Let's try another one. We have another improper integral with infinity in the upper limit. So we're going to set it up as the limit problem. T goes to infinity. The integral is now from -3 to t. And we're going to do this one by substitution, or we can just recognize the formula here, but let's just go with substitution. So dt is -2 dx, dx is -1/2 dt. So the integral that we have is it's going to be e to the t, so it's going to be -1/2 integral e to the power t dt. And I guess this was a terrible choice of the variable for substitution. Let's call it s. So ds, ts. And here we have dss. And the new limits, let's pretend that we don't know what they are. So we don't have to change them. But once you find the antiderivative and replace the new variable with the original variable, you can plug in the limits for the original variable, which are -3 and t. So the limit now becomes the following. So we have -1/2 e to the -2t minus -1/2 e to the -2 times -3. And as t goes to infinity, -2t goes to -infinity, e to the -infinity goes to 0, so this part goes to 0. So the final answer is e to the power 6 over 2. Have e to the power 6 over 2. Let's see if that's the right answer. And looks like we got that right. Let's do another problem. And for this one, we're going to introduce a new variable, let's say t, and we're going to set it up as the limit as t goes to infinity. And we should recognize this problem, and we should be able to set it up and do it with integration by parts. So u is equal to 4x, du is equal to 4 dx, dv is equal to e to the -x dx, and v is equal to -e to the -x. So the problem is the limit as t goes to infinity, it's going to be uv. So we have -4x e to the -x from 2 to t minus integral of v du. So it's going to be plus 4 integral of e to the -x dx from 2 to t. But, so again, we're gonna do one step at a time. Minus, and here we're gonna have negative, instead of x I plug in 2, plus, it's going to be 4 times -e to the -x, evaluated from 2 to t. So the hardest part here is to actually keep track of your own work. Everything else is pretty straightforward. So this one I'm going to write as -4t over e to the t plus 8 over e squared minus 4, and here we have e to the -t minus e to the -2. And as t goes to infinity, some of these expressions become 0. And it shouldn't be too hard to see that this goes to 0 as t goes to infinity, and this goes to 0 as well, and we can show that using the L'Hopital's rule. So the final answer is 8 over e squared plus 4 over e squared. I guess those can be added, actually. Right, 12 over e squared. Let's see if that's the right answer. That's the right answer. So all integrals of type 1 are pretty much the same. So if you have any questions, feel free to reach out.